Hello students and welcome back to my channel once again. In this video, I have come up with certain concepts which are exclusively required for JEE mains and NEET exam, and probably it will be helpful for JEE advanced as well. Okay, but there are rare chances that these things can be asked in class 12 exams. So students who are preparing for board exams class 12, they can omit this video students. Once board exams are over and if you are about to prepare for NEET or JEE mains, only then you see this video. That will be helpful for those students who are preparing for NEET and JEE mains. Okay, right. So already I have posted 3 videos. The last 3 videos you can check based on electromagnetic waves, and most of the topics which are relevant to class 12 part I have already covered. These are few topics, exclusive topics which are relevant only from the point of view of JEE mains and NEET exam. Okay, students. So let us start without wasting time. Now, first of all, you have to understand that light photons, okay, you have to treat them as particles. Okay, so to be treated as to be treated as particles. Okay, so particles, they'll have momentum, moving particles in fact, to be treated as moving particles. So if a moving particle is there, it will have momentum, and its momentum is h by lambda as per de Broglie wavelength. You know this. As per de Broglie's hypothesis, lambda is the de Broglie's wavelength, right, students? Also, we know energy is hc by lambda. So from these two, we can write energy is equal to momentum into c. Okay, students. So a very important formula, or you can write the momentum carried is equal to energy divided by c. I am using the symbol E, and the same symbol E will be used for electric field intensity also. So don't be confused between the two. Okay, students? That is clear? Right. Now, let us talk of energy density. Energy density of an electromagnetic wave. So, energy density is basically we are going to find energy density due to electric field. Okay, this is half epsilon 0 into E square. You might have come across this earlier, okay, in capacitor chapter. Right now, as you can see that this E is actually the peak value multiplied by sine kx minus omega t, assuming that the wave is going along x direction, positive x direction. You can have this. Okay, students? Then, so finally we can write this as E naught square epsilon 0 by 2 into sine square of kx minus omega t. Since E is a time dependent function, you can see, students, time as well as x both. Okay, it is a function of x and t. So therefore, we need to take the average value, averaged over a time period at a certain point. That is, you fix the value of x and then you take the average for one time period. Students, you know how to find the average for one time period. I will write this formula. In general, any time related function, time dependent function, the average value is calculated like this. You integrate the function with respect to time for whichever time interval you want to take the average. Suppose you want to take the average between the instants t1 to t2. Then you have to integrate between t1 to t2 and you have to divide by the time interval. This is how we find the average of a time dependent function. Okay, students? So here also we have to use the same formula, that is, this will be integral sine square kx minus omega. This is the function. So integrate with respect to the t. Suppose you want to find for one complete time period, you have to use this. This, as you know, it will be half. Okay, you already know this. This is going to be half this part. So that is how you get the average. Now we also know that E naught is equal to root 2 times of ERMS. So if you substitute this here, then we have the average energy density due to electric field is epsilon 0 by 2 into ERMS square. Okay students, if I substitute here, 2 gets cancelled. Okay. On a similar basis, it can be shown that the average energy density due to magnetic field is equal to BRMS square upon 2 mu naught. So therefore, the total energy density at a point will be the average energy density due to electric field plus average energy density due to magnetic field, which will be half epsilon 0 ERMS square plus half BRMS square by mu naught. As we know, students, that the electromagnetic wave carries equal energy in the form of electric and magnetic fields. In other words, the contribution towards energy is equally between electric field and magnetic field. So on that basis, we can write this as twice of this, or twice of this, twice of this. Okay, students. So this is the average energy density in terms of electric field or magnetic field. You can also memorize this in terms of the peak value. In terms of peak value, a 2 will appear here. In terms of peak values, a 2 will appear. Okay, students. SI unit will be what? Energy density is basically energy per unit volume. Energy per unit volume. So basically you have joule per meter cube. Okay, students, joule per meter cube. It is always also equivalent to Newton per meter square. Though we will not be using this Newton per meter square, we will be using only joule per meter cube. Right? So I hope that is clear, students. Right. Next, we'll talk of intensity. Intensity of a wave. Okay. So at a point, of course. At a point. So what does it basically mean? Suppose the energy carried by the wave is flowing like this, because as a matter of fact, you know that energy is always associated with the wave. So a traveling wave always carries energy. Here electromagnetic wave carries energy in the form of electric and magnetic field. So the intensity is the energy crossing per unit area, per unit time interval, where the plane of the area is normal to the flow of energy, directional flow of energy. So intensity, I denote it by I, is the energy crossing per unit time. Okay. Energy crossing per unit time is also known as power, of course. Per unit area, the plane of the area being normal to the direction of energy flow. being perpendicular to the direction of energy flow. I hope that is clear. Alright. So now suppose you have an area A here. Let us say area A with its plane perpendicular to the direction of flow of energy. Energy is flowing like this. Let us say E energy flows, okay, during a time interval delta t. Okay. Then we can write intensity as the energy flown per unit time per unit area. Okay. Energy flowing per unit time is also the power. So P is the power. Okay, students. Based on this, we can judge the SI unit here. Okay. So SI unit of I will be based on this. It is joule per second meter square, which is equivalent to watt per meter square. Okay, students. I hope that is clear. I hope that is clear. Then next, we'll see the relation between intensity and momentum. So next is relation between intensity and momentum carried by the photons, of course, of electromagnetic wave. Okay, students. Right. Now here you see, suppose electromagnetic waves are crossing this way. Okay, they are crossing this way. And for now, let us take the area perpendicular to this, perpendicular to the direction of flow. I take the area as A. Let us say the intensity is I. Then now we can see that the energy crossing per unit time, okay, will be energy crossing per unit time per unit area multiplied by area. This is from definition of intensity. From the definition of intensity. And we have seen that the relation between, okay, the relation between P and E, energy and P, is energy can be written as P into C. You can see this. Energy can be written as P into C. So I'll write this as P into C. Therefore, the momentum carried per unit time interval is I A by C. So this formula you have to memorize, students. This is the momentum carried by the electromagnetic wave, that is photons, okay, per unit time, by all the photons crossing per unit time, okay, momentum carried by all the photons which cross per unit time interval across this area, this IA by C. I'll write it total. This is a total momentum carried by all the photons which cross the area, A in unit time interval, that is per second, unit time interval. Okay, students. Right. Next, we'll see the thrust due to this thing. The thrust due to this. So next topic will be thrust due to striking of photons, that is EM wave, electromagnetic wave. Okay, students. Now we'll consider three different situations. Okay, one situation, the surface is perfectly absorbing. In the other, it is perfectly reflecting, and in the third, it is partially reflecting. Okay, this I take it as perfectly absorbing. Perfectly absorbing. That means a photon, as soon as it strikes, gets absorbed. Okay. So suppose photons strike here, perpendicular to the surface. Okay, and I'll take the area as A. I'll take the area as A in each case. So the rate at which momentum is absorbed or momentum changes is this. Because you see, student, initial momentum, let us say it is P. Okay, but once it gets absorbed, the final momentum becomes zero because the photons no longer exist there. So change in momentum will be how much? Change in momentum is P itself. So rate of change of momentum is exactly P by delta T, and we also saw that P by delta T is exactly I A by C. So basically it is I A by C. But as per Newton's second law, we know rate of change of momentum is the force applied. So therefore, the force exerted by all the photons striking the surface is this I A by C. This is the force exerted. You can see force is normal to the surface. Force is normal to the surface. Then next we'll see perfectly reflecting. In case of a perfectly reflecting surface, what happens? You see, initial momentum and final momentum are numerically same, but they are opposite in direction. So suppose initial momentum is P, final momentum is minus P, isn't it? So change in momentum will be, mod of change in momentum will be 2P, P minus of minus P. So accordingly what will happen? The force is the rate of change of momentum. Rate of change of momentum is twice of momentum carried by the uh, electromagnetic waves, and momentum carried by the electromagnetic waves is IA by C. So as you can see that the force has become double as compared to the previous situation. Okay, again this is a normal force. Remember, normal force, that is force acting normal to the surface. Then let us take a situation in which it is partially reflecting. Partially reflecting. And in case if it is partially reflecting, we should know the reflection coefficient. So students, reflection coefficient means the fraction of light reflected. It is the fraction of light reflected. Okay. So if suppose amount of energy incident is E, incident energy, then we can see the energy reflected is E into R, whereas this is the energy reflected. Whereas E minus ER will be the difference in energy which is getting absorbed. So we have to apply both these formulas, students, whatever we have seen just now. Okay. So basically, we will be writing the expression for force due to absorbed part of photons plus force due to reflected part of the photons, total force. So force due to absorbed part is I A by C, where intensity only I minus IR. We can replace energy with intensity here. So I write this as I minus IR, the portion of the intensity which is absorbed by C, whereas for reflected it is twice of portion of intensity you have to consider which is getting reflected, which is IR A by C. So finally, if I take I common, A and C common, I'll have 1 plus R. So this is the expression for force. Okay, the reflection coefficient will lie between 0 and 1. This is for perfect absorbers, this for perfect reflectors. 0 for perfect absorbers and 1 for perfect reflectors. Okay, students, I hope that is clear. Is that making sense? Right. So next, let us see the relation between intensity and area and the energy carried. Okay. So we'll see the relation between intensity and energy carried. So here suppose this is an area. Let us say this is an area. Area is A, and incident light is incident at an angle of, let us say, theta with the normal. This is a normal. So incident light is incident at an angle theta with the normal to the area. Okay, students. So basically, if we consider the area which is normal to the direction of flow, so this angle will also be theta, and this area will be actually A cos theta. And if I take the intensity as I, then I can write that the energy incident per unit time is equal to I into area which is perpendicular to the direction of flow, which is A cos theta. Okay, students? And this can be written as momentum into C upon delta T. So therefore, bringing this to this set, the rate at which momentum is carried, is actually equal to I A cos theta by C. Okay, students? This you have to understand clearly. Now let us find the force exerted on the surface when it is inclined, when the radiation is inclined. So next we will see the thrust, that is force, okay, exerted due to an inclined, okay, wave beam, inclined wave beam. Now let us say this is the area. The area, I have taken the area as A. This is the normal to the area. So light beam is coming like this, or the beam corresponding to electromagnetic waves is coming like this, making an angle theta with the normal to the area. This is the normal to the area. So just now we saw the momentum carried by the wave per unit time interval is this. Okay. Okay. Also, the momentum has a direction. Direction will be in this direction. This is the direction. I draw the direction with yellow color. This is the direction. Okay, students. I hope that is clear. This is the direction of momentum. Now, if this angle is theta, so you have to take the normal component of momentum, which will be p cos theta, because exactly this momentum, this component of momentum is the region of force or thrust exerted on the surface area. Okay, surface area. So therefore, what we can write is this: the what you call momentum component carried by the wave perpendicular to the surface or normal to the surface per unit time will be p cos theta by delta t. But what is p cos p by delta t? We have already found, students. See this. So therefore we can write this as I a cos theta by c into cos theta. Okay, so which is actually equal to I a cos square theta by c. If it is perfectly absorbing, then this will be the rate of change of momentum. If it is perfectly reflecting, then twice of this will be the rate of change of momentum. And if it is partially reflecting, then we know the rate of change of momentum will be this multiplied by 1 plus r. So finally I can write rate of change in momentum. Change in momentum, okay, which is also equal to force, that is normal force. Normal force is I a cos square theta by c into 1 plus r, where r is the reflection coefficient. R is the reflection coefficient. 0 for perfectly absorbing surface, 1 for perfectly reflecting surface, and any value between 0 to 1 for alternate surface. Okay, student? I hope that is clear. Next, let us discuss radiation pressure. Radiation pressure. So it is the pressure arising as a result of the thrust due to the impact of the photons on the surface. Okay, students, as we know that when light is made incident on a surface, basically photons strike the surface. And since photons carry momentum, there is a change in momentum in the photons while they strike the surface. So that change in momentum is imparted to the surface, and hence the surface experiences a force. So this normal force per unit area is the radiation pressure. So that's how we find. So radiation pressure is the normal force per unit area. We have been calculating the normal force, students. Okay, in all the cases, you can see the normal force. If you take the what you call this thing, normal force, it is this. So I a cos square theta by c to a. So a gets cancelled here. So finally we are left with this. So radiation pressure general formula is I upon c into cos square theta into 1 plus r. Here I missed 1 plus r, sorry students. I have to take into account 1 plus r. I have basically used this formula. This formula I have used. Okay. Right. So I hope that is clear. This will be very useful, students, for competitive exams to solve competitive exams questions. Okay, so please keep in mind this important formula. If the light is incident perpendicular to the plane, then theta will be 0, cos 0 is 1, then only I by c into 1 plus r will be there. So I'll write it here. For normal incidence, theta equal to 0, then it implies the pressure is I by c into 1 plus r, which we have already found. Okay, students? Right. Then, next we'll be seeing the Poynting vector. Okay. So this has been named after the discoverer of this vector. So basically, Poynting vector is denoted by vector s. It is simply the cross product of vector E and vector H of the electromagnetic wave. As we know, students, that electromagnetic wave has electric field and magnetic field. Here, H is known as the magnetic field intensity. Magnetic field intensity, or you can simply call it as the H vector of the magnetic field, which is defined as B by mu naught. H vector is defined as B by mu naught. So replacing H with B by mu naught, you can see this is the Poynting vector. Okay. Now as we'll see that it is basically equivalent to energy density. Sorry, intensity. I'm sorry, students. Intensity, as we'll see. Okay. So let us find the magnitude of this. So magnitude means you can see it is 1 by mu naught into E B into sine 90 degree, because you know that the electric field and magnetic field are at right angles to each other. Electric field and magnetic field are at right angles to each other. So sine 90 will be 1. E B upon mu naught. Now we can write B as, we all know that C is equal to E by B. Speed of light is equal to E by B. So B can be replaced by E by C. Okay, students? Alright. But this can be written as twice of E square by 2 mu naught to C. I'll do one thing, sorry students. I'll express in terms of B. Of course, you'll get the same result. It's not a problem. But since mu is already there, so better to have this. Okay. What happened? I'm not able to. It seems it got stuck somewhere. It's not getting operated. So just a minute, students, and again I'll open it. Okay, I'll open it again. Don't worry. Yeah. So I hope that is clear. Yes, it's working. Let me check. Yeah, now it's working. Sorry for the disturbance, students. Please forgive me. Sometimes it happens. Electronic gadgets, you know, they fail to operate sometimes. So I'm extremely sorry for that, right? So what I'm going to do is that I'm going to express this in terms of B. So E can be written as B into C. E can be written as B into C. Then multiply and dividing by 2, I can write this as Okay, students. And as you know, this is basically energy density due to B, and twice of energy density due to B is the total energy density. And total energy density into C, and this is equal to intensity of the wave. Okay, this is equal to intensity of the wave. I'll show you how. Yes, here itself I'll say. Okay, I'll just show you separately. I'll show you, student. Don't worry. Where is it? Now, suppose you have a wave going like this, electromagnetic wave going towards right. Okay, we can take the area as 1, cross section area as 1, and let the wave be here at t equal to 0. Then at t equal to 1 second, it would have traveled a distance equal to how much? Equal to c, that is speed of the wave. Is it, students? That means now you have electric field and magnetic field here. In other words, this volume is now full of electromagnetic wave, and hence it has energy, and the entire energy in this region came from this side, and that should be equal to intensity, because the energy contained in this is actually the energy crossing this area per unit time and per unit area. So this must be intensity. The energy in this must be intensity. So energy in this is energy density in each volume, I mean energy in each volume multiplied by volume. Volume is cross section area into length. Cross section area is 1 and length is c. Cross section area is 1, length is c. So therefore I is equal to uc always, where u is the energy density. Okay, students. So basically Poynting vector magnitude gives you intensity, and you can see its direction is towards vector E cross vector B, and we have learned earlier, students, that vector E cross vector B is directed towards the direction of wave propagation. So Poynting vector is a vector directed towards the direction of propagation. So I'll write as a note so that you remember this. Poynting vector has a magnitude equal to intensity. Okay, and direction of Poynting vector is along the direction of propagation of wave, is along the direction of propagation of wave. Okay. So this is how we define Poynting vector. I hope Poynting vector is clear, students. So SI unit of Poynting vector will be what? Same as intensity. So SI unit of Poynting vector will be same as that of intensity, which is either you can write joule per second meter square, or you can simply write watt per meter square. Any one thing is okay. Okay, students. Next, finally, we'll see the formula for intensity at a point due to a bulb. So intensity at a point due to an EM wave source. I can write like this. Suppose you have a source here. It can be a bulb, it can be a heater, anything which emits electromagnetic waves. Let us say its power is P. Now we have to find the intensity here. at this point at a distance r from the source. This is the source. Now, as we know, power is nothing but the energy radiated per unit time. And as you know, students, this energy gets distributed or spread over a spherical surface of area 4 pi r square. So, intensity is nothing but the energy received per unit time per unit area. Therefore, sorry, it is nothing but energy received per unit area per unit time per unit area. So energy received per unit time is same as the energy radiated per unit time, which is actually the power, and the total area over which it is spread is 4 pi r square. So we get the formula I is equal to P upon 4 pi r square. This is the formula. Okay, students. In certain questions in JEE Mains and Neet, they have asked to find the electric field. Let us say RMS value of electric field you have to find. Then how you can find? First of all, we'll make use of this power upon 4 pi r square is equal to intensity. And just now we saw the formula, students. Relation between intensity and energy density is I equal to UC. So I can be replaced with UC. So I can be replaced with UC. But U is the energy density, and energy density is 1 by epsilon 0 into ERMS square. Total energy density, students. Total energy density is this. You can check. See here, we had already seen the total energy density is how much? Yes. See this epsilon 0 into ERMS square. Okay. So from here you can find ERMS. You can also find BRMS, because once you know ERMS, you can use this formula. C is equal to ERMS upon BRMS. So from this you can find BRMS. Okay, students, and I hope you enjoyed this video. We'll stop here. Okay, thank you so much for watching my channel. Kindly subscribe to my channel and hit the like button. Thank you so much.